All right, so this is a bit different from what might be on your handouts, but I decided to change the topic based on the interest of the audience. So I'm going to talk about this Scala-based machine learning library that we built at Salesforce Einstein. And for a bit of background about myself, I currently lead data science efforts at Salesforce Einstein. Prior to that, I was a data scientist at LinkedIn and at Microsoft. And before that, I got my PhD in computer science from Stanford University. So I thought it would be useful for me to set up some context around all the work that we're doing at Salesforce. As many of you know, Salesforce has this highly customizable CRM platform that businesses use to manage all kinds of customer interactions. So for instance, Uber uses Salesforce to manage all its marketing automation. And so this means that all the email marketing campaigns to its riders and its drivers are managed through Salesforce. Comcast uses Salesforce to manage all its customer service cases. Square uses Salesforce to manage its entire sales process from lead to cash. UCSF uses Salesforce to manage patient healthcare records. So there's literally hundreds of thousands of businesses that are using Salesforce every day to manage all kinds of customer touchpoints. And the problem we're trying to solve is that for the majority of these businesses, data science is out of reach. And why is that? Well, first of all, to do data science, you need to have data. And so to get the data, you need to have a team of data engineers that's ETLing this data for you from all the relevant data sources. And then you need to have a bunch of machine learning PhDs on staff in order to do predictive modeling on top of this data. And then finally, you need to have all the DevOps and infrastructure support to keep all of your processes up and running. So it's extremely non-trivial. And this is what we're trying to solve at Salesforce Einstein. We're building a platform that will make it much easier for all these businesses, all these hundreds of thousands of businesses, to get predictive value from their data without necessarily having large data engineering and data science teams at their disposal. And so that's the context of all the work that we're doing at Salesforce. And in particular, in this talk today, I'm going to talk about Optimus Prime, which is the modeling library that we use in Salesforce Einstein. Some of the characteristics of this library, the reason we decided to call it Optimus Prime is because machine learning is all about transformations. And some of the characteristics of Optimus Prime are that it provides a declarative and type-safe syntax for collaborative feature engineering and model development. And it uses SparkML as the underlying execution engine. But before I dive into the details of Optimus Prime, I wanted to walk you through a little bit of the history of how we got to where we are today. So 2 years ago, we were developing the V1 of this library, and our design considerations at that time were that we wanted to build this on top of Spark and MLlib so that we could use all the nice in-memory iterative computing capabilities that Spark provides. At the time, however, SparkML was still in its infancy, and in particular, the data frames and ML Pipelines API were still being developed. And another interesting thing about our use case was that data preparation in our use case involved repeated aggregations over massive amounts of event data. And so we needed to have a way of doing this really efficiently. So what we ended up doing was we essentially built our own ML pipeline interface that operated on RDDs. And we developed our own data transformer interface and our own execution engine in order to optimize how these repeated aggregations were executed. Now, what happened in the meantime was that SparkML just kept getting better and better because there was an active community of contributors that was making it more and more awesome. And when we looked at their APIs, we felt that they'd really nailed, they really had the right set of abstractions. Everything was either a transformer, an estimator, or a pipeline. And we wanted to be able to leverage all of this awesomeness. But at the same time, we felt that it was still less than ideal for our use case, which was large-scale collaborative feature engineering and model development. And in particular, in the Salesforce use case, it's not going forward. It's stuck. Oh, there we go. In particular, in the Salesforce use case, we're dealing with lots of very structured data with a very rich schema. And we have many different teams. And so what this means is that we want to do lots of really rich feature engineering on top of this data. And at the same time, we want to do this feature engineering in a reusable way because we have many different teams that are all developing a variety of different predictive apps on top of these common data sources. And so we don't want to have 20 different teams developing 20 different implementations of TF-IDF, each of which are a little bit buggy. So we want a lot of reusability. And then we also want another interesting thing about our use case is that the developers who are using this platform do not necessarily have deep SparkML expertise, right? So what this use case requires is that we provide a very simple declarative type-safe syntax that makes machine learning development easy in the company. And so this is why we built Optimus Prime V2. It's a developer-friendly interface for non-expert users. And this time we were careful to not reinvent the wheel, so we used SparkML as the underlying execution engine. So now I'm finally going to get to some code, and Vitaly, my boss, asked me to apologize for only getting to the code at slide 13. But I think it was useful to set up some context here. And again, the slide is not going forward. Why is that? Okay.
You just exit the
exit?
presentation. Yeah.
All right.
And then go to that slide and start at that slide.
All right. So apologies for that. So all of the code examples that I'm going to show now are going to use the Titanic dataset. It's a very morbid dataset that's often used in machine learning examples. It's a data set that has all the passengers who are on board the Titanic, and often the machine learning use case is to predict survival. And some of the features that are in this data set, this is a sample of the features, are the passenger class, the passenger's age and gender, the number of siblings and spouses they had on board, the number of parents and children they had on board, the passenger fare, and so forth. So let's take a look at the new syntax. So first, in order to show the benefits of the new syntax, let's look at how you would define features in SparkML. So if I wanted to create a new feature in SparkML that's based on these existing features in the data set, and this new feature I want to create is the family size of the passenger on board. So I want to sum up the number of siblings that the passenger had on board and the number of parents that the passenger had on board. This is how I would do it. So in SparkML, I would first create. Can you see that font? Okay. In SparkML, I would first create a function that takes two integers and sums them up. I would then register this function as a UDF. And then I would transform my training data frame by applying this UDF to these columns, to the siblings column and the parents column. And notice here that I have to be, I'm referencing these two columns by their names. So I have to be very careful that I don't make any spelling mistakes here, that I know exactly what the names of these columns are. I also have to be careful that these are actually integer columns, because if they're not, I'm going to get a runtime error. And then I have to also keep track of all the output column names that I'm generating. And then the other interesting thing here is I'm actually mutating the underlying training data frame. So if I want to apply the same transformation to my test data, I have to be very careful to copy over the same code and not make any spelling mistakes. So it's very error prone, and a lot of errors are only caught at runtime after your pipeline has been running for an hour. So in contrast, in Optimus Prime, this is the syntax that you would use for defining a new feature. You would say that the family size is a numeric feature that is obtained by applying that function to data of type passenger. And so there's two interesting things over here. We've introduced the notion of a feature, which is essentially a type-safe pointer to a column in the data frame. And that's what gives us all this type safety. And the other interesting thing here is that it's not mutating the underlying data. It only depends on the type of the underlying data. So you could apply the same feature definition to any data of type passenger. And there's a very clean separation between feature definitions and data. Now let's take a look at how you would do feature transformations. So going back to the SparkML world, if I wanted to create a new feature, which was the normalized family size, this is how I would do it. I would create a new normalizer. I would set the input column to be my family size column and set the output column to be a new one. I would then fit this normalizer to my training data, and then I would transform the training data. And again, I have to be very careful that I haven't misspelled anything here, that I correctly copied over the name of the previous output column and so forth. So in contrast, in Optimus Prime, this is what you would do, and I think I'm stuck again. Oh man, okay. Wow. Sorry. Yeah. Let's go to the next one. All right, so in contrast, in Optimus Prime, I would create a new normalizer where I set the input column to be the family size column. But the nice thing here now is that I have a val. The family size is a val. There's no chance I'm going to make a mistake when I'm referencing it. And the other nice thing is that because family size is this strongly typed numeric feature, I can create these nice set of transformer shortcuts. And so I can shorten this to family size.normalize. And similarly, if I had a feature such as the age, another numeric feature, I could have another feature that was the age times the family size that I would define with this very nice, simple, intuitive declarative syntax. And so, so the type safety has, sorry, go on.
Are you saving the metadata somewhere and what the min-max is for the
Yes.
size?
Yes.
So
Are we saving the min-max somewhere? But at this stage, it's all definition still, by the way. We haven't run the pipeline. When we actually run a pipeline and save it, that's when we save all that information. Oh, the question was, do we save the min-max and everything that's needed for normalizing? All right, so type safety has really provided, it's a reduction in runtime errors, and it's also provided this really nice intuitive declarative syntax. And the other nice thing is you get compiled, as you're editing your code, you can get code completion in your editor because the Scala compiler kicks in. But what the type safety has really provided for us is transparency around what are the inputs and outputs that are expected at every stage of your data transformation pipeline. So for instance, let's go back to SparkML. Say I wanted to create a new logistic regression model and fit it in my data. This is how I would do it. I would say I want to make a new logistic regression estimator, fit it to my data frame, and take that fitted model and use it to transform my data frame. Now, does anyone have any idea what inputs this estimator expects? Any guesses? So if you dig through the documentation, you'll find that it expects that the underlying data frame has two columns, one called features and the other called label. Does anyone have any idea what outputs it's going to produce?
Prediction.
Close. So if you run it and you materialize your data frame and you look at your outputs, you'll see that it produces three new columns, vector, vector, and numeric, called probability, raw prediction, and prediction. So it's this kind of thing can lead to a lot of tribal knowledge that's needed, and it's not very easy to get started. And so in contrast, in Optimus Prime, thanks to the type safety, and I'm stuck again. Wow, this is, sorry. Yeah, so in contrast in Optimus Prime, this is how I would define the logistic regression estimator. I would set exactly the input columns that I want, and thanks to the type safety, I know exactly what output columns to expect, a tuple of three features, vector, vector, and numeric. And so really, the syntax has provided us with four main things. First, a very clean separation between the feature definitions and the data. Second, type safety, which means a reduction in the number of runtime errors, and also very nice things such as code completion while you're actually writing your code, so a lot of improved developer productivity. Third, it has the third thing that it's provided is this really nice syntax where you can have shortcuts for your transformers. And finally, and perhaps most importantly, it's provided transparency around what are the inputs and outputs that are expected at every stage of your data transformation pipeline. But so then how does this all actually run? As I mentioned before, we use SparkML as our underlying execution engine. And so all of our Optimus Prime, did it just go upside down? Wow, what is going on? And now it's like gone. Wow. I have no idea what's going on. All right, so the other, so what happens is under the hood, all our Optimus Prime pipelines actually translate to SparkML pipelines. So SparkML has essentially these two fundamental concepts of transformers and estimators. A transformer is something that takes a bunch of data frame columns and produces a new column. And an estimator is an algorithm that's applied to a bunch of columns to produce a new transformer. And so a SparkML pipeline is essentially a bunch of these transformers and estimators stitched together. And our Optimus Prime pipelines are essentially a wrapper around all of this. When you use our syntax to declare your Optimus Prime pipeline and then actually execute it, what happens is under the hood, it automatically creates the DAG of all the SparkML transformers and estimators that need to run, creates the SparkML pipeline, and then runs that. So we've left it as SparkML to optimize the execution of these pipelines. And what this has really enabled, the way in which this has made, the way in which this has transformed development at Salesforce is that it has enabled much more collaborative feature engineering and model development. And this is because of the clean separation. Wow. This is strange, no?
Now we're expecting that. If it doesn't invert.
If it doesn't invert, it's weird. Okay.
Save as the image. Save those things as the image.
Yeah.
You could also just make that bigger. And not,
Okay.
yeah, or you could save it as a PDF right now. That might help.
Okay. Oh, sorry. Let me. Yeah, let's just finish it off. Yeah. So for instance, because of this nice separation that we have between the feature definitions and the underlying data, we can create this object of our Titanic features where we just list all the features that we want to use. And so now, jeez. And so if I want to now use those features, some of those features to create a new model, I would just import the Titanic features. And a new model is basically just, go ahead.
With your question equation, you never listed what were your input features. Were you just assuming it was like
No, it did.
transformed?
It did. I set the input features explicitly to be survived, and I don't want to go back because I don't want this.
Okay.
So the new model, a new model would basically be just yet another feature transformer that I can contribute back to this repository, and people can use it without having to understand the details of how this model was built. And the other thing, so basically this has bootstrapped the development of new models, which is very useful in our environment where we have many different developers building many different apps on top of these common data sources. It's also tremendously improved developer productivity because of the runtime, because of the compile time checks. And all of this was possible because of type safety. So if you want to find out more about how, it's not going forward. If you want to find out more about how we actually built all of this, you need to stay till the end of the day. And someone from our team, Matthew Taubman, is going to be talking about how we actually built this. So, and I really wanted to go to the next slide, so I'm going to exit again.
You can maximize the window and just do it off the window.
Wow. Okay, never mind. So what I wanted to say is that we're okay. Okay. So what I wanted to say is that this is just a small piece of all the work that's going on at Salesforce Einstein. And so if you're interested in knowing how Prediction.io and MetaMind and Heroku, everything fit together under the Salesforce Einstein umbrella, please email us, reach out to us at einsteinrecruiting@salesforce.com. We're way over time.
Yeah, it's tough on you, huh?
Yeah, go ahead.
Is any of this open source?
We're planning to, it's not yet, yeah. Is any of this open sourced? Not yet, but we would like to eventually.